Chapter 16, Section 3, Chapter 17, Section 1. Electric field strength. So we know electrical forces exist in a field, just like gravity does. In fact, we're going to be able to compare some of our understanding with gravity to electrical things and hopefully help make the electrical things clear. They behave like gravity in some ways. So what's an electric field? The region where an electric force on a test charge can be detected. How do I know if there's an electric field somewhere? Well, if I have something that is charged, we call it a test charge, and it is in that field, that test charge will feel a force. It will either be attracted or repelled, depending on what the signs are. So there's an electric field anytime, if there's a test charge, if it feels a force there. The SI unit for the electric field is newtons per coulomb. So the strength of an electric field is the force you feel per unit charge. And remember, charges are measured in coulombs. So newtons per coulomb. The direction of the electric field vector, and we're going to use capital E, is the direction of the electric force that would be exerted on a small, what's that next word? Positive test charge. So here's the idea. I think of a positive charge to know what direction my electric field is. If I say my electric field is in this direction, that means that is the direction a positive charge would want to move. So if a positive charge would want to move in this direction, then maybe somewhere over here I have what sign of a charge? A positive, because it's being repelled. So an electric field, the arrow for an electric field is the direction that a positive charge would go. And we'll want to keep that in mind as we see our first exciting video, newly released. Let me get the volume turned up. Well, maybe not newly released, but...
An electric field is a region of space around a charged object in which a stationary charged object experiences an electric force because of its charge. The electric field at a point is defined as the electric force that would be exerted on a small positive charge, called a test charge, located at that point. The electric force, like any other force, is a vector quantity. The strength of the electric field at a point is defined as the magnitude of the force acting on the test charge divided by the charge of the test particle, which is always positive.
So force is newtons, charge is coulombs. There's your newtons per coulomb electric field strength.
The direction of the electric field at a point is defined as the direction of the electric force that would be exerted on the test charge.
So without seeing this big Q for a big charge over here, if I see this electric field arrow, I know that my positive will go in the direction that that arrow goes. So I'm going away from some location. Here, I'm going toward, so I'm attracted to some location. So that's why that one looks negative. All right, hopefully that's pretty straightforward for us. Electric field strength, then, is going to depend on two things. It's going to depend on the charge and the distance we are away. Bigger the charge, the bigger the field strength. The closer we are, the stronger that field strength is going to be. Same thing with gravity. The closer I am to a mass, the stronger that gravitational force is going to be. So electric field strength due to a point charge, here's our next formula. Electric field strength, Coulomb's constant, times the charge producing the field, divided by my distance squared. Closer I am, the stronger that electric field strength is. Farther away, the weaker that electric field strength is. Calculating net electric fields.
Consider two small charges, one positive and one negative.
Try to make me work.
Using the superposition principle, you can calculate the net electric field at any point. Choose a point P directly above Q1. First, calculate the electric field produced by each charge at point P, and then find the vector sum of these fields.
So if I want to know what is my electric field strength at this point right here, okay, well, I'll need to figure out from each of those charges to that point.
Remember that the electric field at a point is the electric force that a small positive charge would experience at that location.
And that tells me the direction. So this, at that point right here, it's going to have an electric field that's moving towards that point. Between this other positive, the electric field is going to be going away from that point.
The magnitude of the electric force exerted on the test charge by Q1 is given by Coulomb's law. Q1 and Q0 are both positive, so they repel each other. Since Q2 is negative, the force it exerts on Q0 is attractive. The strength of the electric field at point P produced by Q1 is the force divided by the charge Q0. The strength of the electric field produced by Q2 is found by an identical procedure.
So there's that formula we just saw. Coulomb's constant, the charge that's producing it, divided by the distance squared between them.
The forces on the test charge have been replaced by electric fields at a point in space. Now the x and y components of each electric field can be found separately. Then the components can be added to give the x and y components of the net electric field, which are shown here. These components can be added by drawing them to scale on graph paper. E tot, the magnitude of the net electric field, can be measured with a ruler. The angle phi, the direction of the net electric field, can be measured with a protractor.
We're not going to be doing it graphically. How are we going to find, I love how they said E tot, the total electric field, the resultant. How are we going to find that? We know these two components here. Yeah, Pythagorean theorem. How are we going to get this angle? We know these two yellow components. The inverse tangent. Yeah, we're not going to be drawing at the scale and trying to do a protractor.
Usually, however, the Pythagorean theorem and the arctangent function are used to find the magnitude and direction of the net electric field.
All right, so let's try it out. Page 565, number 2. See if we can make one of these problems work. A proton and an electron in a hydrogen atom are separated on average by about 5.3 times 10 to the negative 11th meters. What is the magnitude and direction of the electric field set up by the proton at the position of the electron? So we have a proton right over here, so that's a positive charge. And we have an electron right over here, and we know that's a negative charge. And then they told the distance between was, thank you, 5.3 times 10 to the negative 11th. Meters, I hope it was in meters.
Yes.
Yeah. All right, was it meters? So they want to know what is the magnitude and direction of the electric field set up by the proton at the position of the electron right over here. So we want to know what is the electric field at this location. So look at your notes. What equation do we have for electric field? Yes, think of one after that.
Oh, Coulomb constant.
Coulomb's constant. Charge producing it, divided by the distance between it squared. The proton is the charge producing it. So we're not going to be using the electron, we're going to be using the proton. What's the electric field strength at this location right over here? They also want the direction. Well, no problem. Well, maybe I guess we better find out what is the charge of this proton. So, what's the charge of a proton? It's positive. Positive what number?
1.6 times 10 to the negative 19.
It's the same charge of an electron, it's just positive. Electron is that number, just negative. And here's our R, right over there. So Coulomb's constant, 8.99 times 10 to the 9. Times our charge, 1.6 times 10 to the negative 19. Divided by the distance between them squared. 5.3 times 10 to the negative 11th, and that has to be squared. This will give us the strength. We'll figure out the direction in a minute. So this is always a little bit of a challenge, trying to get our calculators to cooperate. What'd you get, Jack? So as you keep entering it, see if you can also get 5.1 times 10 to the negative 11? Positive 11, negative? Positive 11. What unit?
N/C.
Newtons per coulomb. Now, what direction is this electric field experienced by from this?
Going towards.
Okay, describe it to me in reference to the proton, which is the one producing the charge.
Oh, the electron is going there. Okay, this is better.
All right, here's where we have to be a little careful. Remember, the direction of an electric field is the direction a positive charge, a positive test charge would feel. So if I have a positive test charge out here, what direction would it feel a force?
Right.
Away from that proton, right? There we go. So ignore the fact that right over here they said there was an electron at that position. The electric field direction is based upon what a positive charge would do. So away from proton. That might be a good way to describe it. Now I'm going to add a little bit to this problem because they didn't do quite enough for this combining to get a total field. So let's say we add something else. Let's add right over here an electron. So I'm going to have a charge, negative 1.6 times 10 to the negative 19 coulombs. And let's say that the distance here to here happened to be, what shall we make it? 3.1 times 10 to the negative 11th meters. I want to know the total charge felt at this position right here. Well, we already have one answer. This is what the proton does at that position. So what does this electron do at this position? Well, I am going to need to know this distance. Well, that's a right angle right now, right there, how I drew it up. 3.1 is this left leg, the 5.3 is that leg over there. So to get this distance, I'll call it D right down there. What am I going to do to get that distance? Pythagorean theorem. I'm going to take the square root of you are going to take the square root of 3.1 times 10 to the negative 11th squared plus 5.3 times 10 to the negative 11th squared. So what is the distance between that electron and our position?
6.1.
6.1 times 10 to the negative 11th. So that is our new radius, if you will. So I can use the same formula right up here, and let's get the electric force based on this electron. So my distance, or my Coulomb's constant, is still 8.99 times 10 to the 9th. My charge is well, I don't even care whether it's negative or positive. I guess I'll put a negative 1.6 times 10 to the negative 19. And my distance is that 6.1 times 10 to the negative 11th, which we have to square. So what electric field strength do we feel from that electron?
Negative 3.87 times 10 to the 11th.
Okay, I'm just going to write the magnitude. 3.8 or 9?
3.9.
3.9 times 10 to the negative 11th? Positive 11. Newtons per coulomb. So let me come back up here. I'll do it in green. At this point, the electron, at this point, I have a force of, where was it? 5.1 times 10 to the negative 11. Positive 11th. I keep on wanting to call it negative. In that direction. Now this is a negative charge, so a positive test charge would be attracted to it. So it's going in this direction at 3.9 times 10 to the 11th. I need to combine these two. Now I'm going to redraw them over here because I had things all on top of each other. So right over here is my 5.1. We'll remember that's at 10 to the 11th. And right over here is a 3.9. Now if I'm going to combine these, I need to resolve this one that's at an angle into its two components. So I've got to get that angle right there to resolve them, which is the angle right there. How am I going to get theta? How am I going to get that angle? Inverse tangent of what? Opposite 3.1, and I can drop off the 10 to the negative 11 because they're both the same. When I divide them, they would just cancel. And the adjacent was 5.3. What angle do you get? Make sure you're in degree mode. 30.3. So I know my angle here is 30.3 degrees. So how am I going to get this component of that 3.9? How will I get that component down here? The hypotenuse times the cosine. 3.9 cosine of the 30.3. So 3.4?
Yeah.
So I get 3.4. Now I know it's times 10 to the 11th. I also need to get this component. I'll use the sine. 3.9 times the sine of 30.3. How much? Maybe you're right. 3.9.
2, yeah.
2.0?
Yeah.
Maxwell, 2.0?
2.0.
All right.
I was scared.
2.0. Now, I am needing to combine all these horizontal and vertical. These two are horizontal. See if I can keep you focused. That I need to combine. Now, they're moving in opposite directions. So what do I do to get the total horizontal with the 5.1 and the 3.4? Subtract. What's 5.1 minus 3.4? 1.7. I needed more space on my paper. So here we go. From this point to the right, I have a 1.7 times 10 to the 11th. Now my vertical is 2. That's the only vertical. So I'm going to go ahead and draw in my 2, end to end. There's my 2.0. Now my complete result will be this one. That E tote that they said a little bit earlier. There's my complete result for it. So you tell me, what is the resultant electric field strength? How will I get it? It's just the hypotenuse of a right triangle. Use the Pythagorean theorem. Go ahead and do that. Square root of 1.7 squared plus 2 squared.
2.6.
2.6? 2.6 times 10 to the 11th newtons per coulomb. That's my strength. And now I need to know, what is my angle? How am I going to get that theta? Inverse tangent of 2 over 1.7.
Yeah.
49.6 at 49.6 degrees. we could maybe say above the positive x-axis. That might be a description for it. So there is, now I added to their problem. They just asked one question. But there's how we combine them all together. The book gives you another example on page 564. That's how we combine them together to get our complete electric field strength and what direction is it going. All right. How do we draw these electric fields? Well, they're called electric field lines. And the number of electric field lines that we draw is going to be proportional to the field strength. So at any diagram where you see more, and if you turn in your book, a good place to be looking now is 566 and 567. When you see more lines per given area, it means it's a stronger field right there. Positive charges will use plus q, and negative charges will use negative 2. And electric field vectors, remember, go in the direction that complete that sentence. Positive charge would move. And our electric field lines, they're just little lines with arrows on them, so we can see the direction that they are going. So we'll let them talk about the rules over here. Rules for drawing.
Electric field lines are a way of visualizing electric fields. For an isolated positive charge, the lines originate on the charge and continue to infinity. For an isolated negative charge, the lines originate at infinity and terminate on the charge. When two or more charges are present, the field lines still obey the same simple rule. The number of lines leaving a positive charge or terminating on a negative charge is proportional to the magnitude of the charge. The third and last rule is that the lines of the same field cannot cross each other.
So we are going to be perpendicular at the surface. I don't know if you can tell that or not, but they're going to be perpendicular at the surface. Lines are going to be proportional to the charge. These are both positive, these are both magnitude of two charges. If you counted the number of field lines that left this positive 2, now why are the lines going away from that positive charge?
Charges go in all directions.
Because electric fields go in the direction a positive would move, right? If I had a positive charge out here, it would be repelled by that positive, which is why these by the negative 2 are coming in. Because the electric field is the direction a positive would want to move. It would be attracted to that. If you counted the number of lines that were leaving this positive 2 charge, it would equal the number of lines that are arriving at that negative 2 charge, if they drew it right. So right over here, there's 2 similar charges. And so you can see what the electric field would look like. And if you had a little positive test charge, and you could drop it on one of these lines, it literally would follow the curve that they have drawn right there. That's the direction the force would be moving them. So let's do several charges here. See if we can
For
make that
two
work.
equal and opposite charges, the number of lines that begin at the positive charge is equal to the number of lines that terminate on the negative charge. Near the charges, the electric field lines are nearly radial. The electric field is strongest in the region between the charges, which is indicated by the high density of field lines.
Electric field strongest right there because it's the highest density of lines. It's much weaker out here.
For two positive charges, the field lines originate on each charge and continue to infinity. Again, close to either charge, the lines are nearly radial. In this case, the electric field has a minimum in the region between the charges, which is indicated by the low density of field lines.
So these essentially are canceling each other out because they're both trying to repel, and so if I have 2 opposite vectors, I'm in equilibrium. So it's 0. There is a place, in fact, right there in the middle where there is no electric field strength, or the force is 0, the strength is 0 right there.
If both charges are negative, the representation of the field will be similar, except that the lines will originate at infinity and terminate on the charges. The field created by a negative particle and a positive particle with double the charge resembles that of the equal and opposite charges, except that only half the lines originating from the positive particle terminate on the negative charge.
Count for me real quick the number of lines leaving this positive 2. I'll put my arrow somewhere for reference.
You like
16? I think it's 16. Count the number that are arriving on that one. You just told me a number without counting.
No,
But you're right.
Yeah.
8. It's going to be 8.
8.
Oh, never questions you. 16 of them are leaving, 8 should be arriving. The ratio of the charges. So there's a specific way to draw those. They're all drawn correctly. All right. Conductors in electrostatic equilibrium. The electric field is 0 everywhere inside a conductor. If I have a metal wire, let's make it a metal rod so it's bigger, that is charged, statically charged, there is 0 charge inside that rod. All the charges are residing on the outside, which is why on your electrostatic lab you did last time, you had that, we call it a Faraday cage. It's just a metal cage, it's a conductor. So that any charges will be residing, any charges in the air, it helps. It wasn't totally covered, but if it was, it helps keep all the charges on the outside of that conducting structure, that cage. I mentioned the other day, a car protects you in lightning because of the metal cage you are inside of. The charges are all going to be running around the outside of that metal cage. They should not come through that metal cage. They should all be on the outside. And when I say shouldn't, they won't. But I hate to say never 100% with everything, but they won't. They'll be on the outside. That's what keeps you safe. If you are struck in your car by a lightning bolt, those rubber tires do absolutely nothing for you. That lightning bolt would go around the car and jump straight to the ground. Doesn't matter whether the rubber tires there or not. It's just going to jump. So the rubber tires don't protect you. It's the metal cage that protects you. Excess charge on isolated conductors reside on the outer surface. I think I already said that one. But the third thing, the electric field just outside a charged conductor is always perpendicular to the conductor surface. We kind of saw that on the drawing, those field lines. Now, if I have a spherical conductor, like those Van de Graaff generator globes back there, they're not perfectly spherical, but the idea is to keep them spherical because I can build up the largest charge on a sphere. If it's irregularly shaped, those charges will accumulate or collect on the sharpest points. When they say the radius of curvature of the surface is smallest, that's the sharp points. They will collect on the sharp points. Now we're going to see some demonstration of that. And the first thing I'm going to show you is a large Tesla coil, much stronger than mine, and a person inside a Faraday cage. So let's hit the lights.
Near-death cage experience.
Yeah, it's not really a near-death cage experience. But I'll let this play here, and we'll leave it at this size because that way it gets recorded for your friends. Try that again. And we'll try the mouse. He is inside that cage. Do not touch the outside, do not touch the cage. Now that acts just like lightning. Notice it jumps all around. You would think it would always strike the closest point, but it doesn't. Sometimes hits the ground, sometimes up towards the ceiling, sometimes the corner. I mean, it just jumps all around. It always will take the path of least resistance, but we just don't know where that is at any given moment in time. If you are inside a Faraday cage, a metal cage like that, you're perfectly safe. Oh, it's really bright, yeah, but no, it's not that bright, like a welding, where it will damage you. It doesn't do that. So let me tell you 2 lessons from this. Lesson number 1 is unless you have a Faraday cage or you're inside a metal cage, you should not be outside in a lightning storm. So recently on campus, we had this pretty good storm that was on a Thursday night when I was out on supervision. And what do I see? I see a couple of students sitting out there on the benches admiring the lightning. Now, I love lightning too. I love to admire lightning. I think it's really cool. I love to take pictures of lightning when I get a chance to. But that is extremely unsafe. So you're sitting out there on the bench and you might be thinking, look at these big trees. Look at those metal flagpoles that are behind me. I'm safe. I'm not going to get struck by lightning. Did you see there where that was jumping all around? It did not always go to the closest metal structure. Lightning will not either. So anytime, essentially what it is anytime there is a lightning strike within 10 miles of where you are, you should be indoors. And so that's what we do when there's lightning around. We'll look at, you can get cool apps on your phone that tells where the lightning strikes are. And if it gets too close, then we go in. Now, why don't you leave your electronics up front again? It's a trap. It's a trap, yeah. So let's look here just a little bit about what's going on. Here's my house. Here's my lightning rod that's sitting right up here. And when lightning comes, hopefully it strikes right there. And they would have a wire that comes down the side of the house and it's grounded into the ground right over there so the power comes. But the goal is that it bleeds off the charge. So we get this charge separation. Maybe this cloud becomes all negatively charged and the ground underneath it is positively charged, the house is positively charged. But the idea is we bleed off the charge, just like we were right back over there. And how do clouds get their charge? It's very similar to what that is doing. Friction is going by, my hair and the balloon. Well, inside the cloud, we've got these winds that are just moving particles up and down inside there. So that's one of the ways where it charges.
Resistance does count as friction.
So it's friction, yeah. When we were building our house, setting in one of the bedrooms, one of the contractors left a little air compressor sitting out there. And he left the cord going out the window, but he unplugged it from the power, which when you're building a house, it's not in the house, it's that electric pole that's close by. He unplugged it. There was an electric storm. And lightning somehow found that generator that was sitting there. And there is metal rebar inside concrete, and that evidently was the attraction. And it blew a hole in the corner of the floor. That's a picture that I took the next morning when I went out there. And it's like, what in the world? And I got a little closer, and that's the concrete that's been blown apart by that lightning that struck it. And there's a chunk of concrete that was knocked off. And you can see the black that is burned right there from, yeah, you can get your stuff. You can see the black that is burned right there. Oh, you can leave your stuff. I'll just collect it later. So lightning is cool, but it's not something to be playing around with. Yeah, Benjamin Franklin did it.
Yeah, he's dead.
All right, chapter 17, section 1. Moving on to the next topic. Electric potential energy. Make sure you read these sections. We just hit the highlights when we discuss and go over these things. Look on page 580, by the way, and they have this real cool testicle picture firing off there. All right, electric potential energy. Potential energy associated with a charge due to its position in an electric field. Think of gravitational potential energy for a moment. Remember, gravitational potential energy was associated with a mass and its position in a gravitational field. When I was farther away from my mass, I had higher gravitational potential energy going on. Well, electric potential energy is very similar. We just have a charge in an electrical field. So electric potential energy is a component of mechanical energy. So here's some of the things we've already learned about mechanical energy. If we take whatever kinetic energy there is, add whatever gravitational potential energy there is, or any elastic potential energy, plus now our electric potential energy. Well, we know kinetic, 1/2 mv squared. We know gravitational, mgh. We know elastic, 1/2 kx squared. So we're going to get an equation for electric potential. And here we go. Electric potential energy can be associated with a charge in a uniform field. So the electric potential energy is negative of the charge times the electric field strength, there's E, times D, our distance we are from some reference point in that field. When we're talking about gravity, it's the distance we are from the center of mass that's producing it. Well, here there's just some position that we want to know. What is our potential compared to that position of the electric field? So electric potential energy.
When two charges interact, they exert an electric force upon one another. The potential energy associated with this force is called electrical potential energy. It is a form of mechanical energy that increases as the magnitude of the charges increases and decreases as the distance between the charges increases. In a uniform electric field, the electrical potential energy of a charged object is due to its position with respect to the direction of the electric field. Displacement of the object perpendicular to the electric field does not change its electrical potential energy. Charges that are allowed to move freely will move to positions of lowest potential energy.
Just like
In the
falling.
device shown here, the electrons exit the central sphere and move to the outer sphere. As this happens, the electrons lose electrical potential energy in exactly the same way that a falling object loses gravitational potential energy. If a person touches the outer sphere, the charge can then pass from the sphere to the ground, where it reaches an even lower potential energy. Charge naturally flows in the direction that results in the lowest electrical potential energy.
I got one of those little things. I'll have to bring it in today. I forgot to bring it in. Potential difference. Let's go back to gravity a minute. If I want to have this mass above the floor, then I can get how much gravitational potential energy it is compared to the floor. Or I can move it over to the table. How much gravity potential energy to the table there. Naturally, it moves in the direction that lowers its potential energy. So we saw the electrons do the same thing. Well, between any two positions in a field, whether it's an electric field or gravitational field, there is a change in potential energy between those positions. So that's what we're talking about here. Potential difference, the change in potential energy between two positions. Electric potential equals the work that must be performed against electric forces to move a charge from a reference point to some other point in question, divided by the charge. So I can change the potential energy if I take this charge and I move it from this point to that point. I have changed its electrical potential. And whatever work I do in doing that movement is how much electric potential I have given to it. So here's another cool equation to write down. V is the letter we use for electric potential. I was like, what in the world do we use V for? Volts. That's what V is going to be standing for. Electric potential difference is measured in volts, or the voltage. So that's what the V is there for. So potential difference, did I just copy this one twice? No, I didn't.
There's difference in a uniform electric field.
Equals the work that must be performed against the electric forces to move a charge between 2 points in question, divided by the charge. That's just exactly the same. That's why I thought it was the same thing. So potential difference. Now these formulas almost look the same, except they're saying the difference in potential is equal to the difference in electric potential energy divided by my charge. So that little delta there is the only difference between those two. And really it's the delta one that we are going to be using. Delta V is measured in volts. Potential difference is the word we say. What's the potential difference for that battery? It's 1.5 volts is the potential difference for that battery. What do we mean potential difference? It's the difference in potential between the positive and negative terminals. That's the difference that we are measuring. So let's see a little video on our potential difference.
If a positive charge is released from rest in a uniform electric field and moves a distance d, there is a change in the electrical potential energy of the charge because of its displacement. The reference point or 0 point for electrical potential energy must be chosen. Here the reference point is point A. If the charge returns to point A, its change in electrical potential energy is 0 because the displacement, delta D, is 0. Only the difference in potential energy is physically significant. The equation for the electric potential energy of a charge Q in a uniform electric field E shows the simple dependence of potential energy on Q, E, and delta D. Just as the gravitational potential energy of a mass falling through a gravitational field decreases, the electric potential energy of a positive charge moving in the direction of an electric field also decreases. Since potential difference is defined as potential energy per charge, the expression for potential difference in a uniform electric field is the potential energy divided by the charge. In this equation, displacement is taken to be in the direction of the electric field. Displacement in a direction perpendicular to the field produces no change in potential energy.
So that's something they pointed out before when they showed it. If I move this charge perpendicular to this field, it doesn't change its potential energy. It's only if I go with the field, I lose, or against the field, I gain. Jump. Potential difference in a uniform field varies with the displacement from a reference point. This is the equation, another one to write down, that they showed you on that last video. Now I'm going to give you a little bit of pre-good news. In this next test, we have so many formulas, I'm actually going to let you have a formula sheet for some of the things. Not all of them, but for some of the things. So copy down these formulas as we come across them. Some of them I'll let you just have a formula sheet for. Let's practice here on one of these. 585, number 2. 585, number 2. It says, what is the potential difference between the initial and final locations of the particle in problem 1? Oh, they're going to make us go back and look. So a particle moves 10.0 meters. So there's a displacement. 10.0 meters. Along electric field strength, 75 newtons per coulomb. So that's our capital E. 75 newtons per coulomb. And they say its potential energy decreased by 4.8. Delta V, potential difference. Potential energy decreased by 4.8 times 10 to the negative 16th joules. That's not V. That's the potential energy that we changed. 4.8 times 10 to the negative 16th. So energy is measured in joules. Part 2 says, what is the potential difference between the initial and final locations? What's the potential difference formula? Guess I didn't even need that other one down there, did I? Negative electric field strength, 75. Times the distance that we moved, 10 meters. Get out your calculators. Negative 750. What's our unit? Volts. That's a clue right over there. Volts. Potential difference is measured in volts.
Why do we need the delta?
We didn't. I was collecting information from problem 1. but I didn't need that information, so I'll just erase it, because our equation that we used just needed electric field strength and how far it moved. So it lost 750 volts as it moved between those two locations. Potential difference continued. So diagram on the right there, the electric potential at point A depends on two things: how strong my point B charge is and how far away I am from that charge. Electric potential exists at some point in an electric field regardless of whether there's a charge at that point. So they show a charge here at point A. But if this is just a location without a charge there still is electric potential energy because I'm in a field. At point B, there's a charge, so I'm in an electric field. So there's electric potential energy here regardless of whether there's a charge at that location. When we talk about reference points for potential differences near a point charge, we talk about coming from infinity. Ready for your next formula?
Give me more.
The potential difference between a point at infinity and a point near a point charge is, here's this formula. And this is the reason why I'm going to let you have a formula sheet for some of these. I'll tell you some that I want to have memorized before the test, so you'll know of the things you've written down, what you need to have memorized. So potential difference there, Coulomb's constant times the value of that point charge and how far away are we at the point charge. That's going to be the potential difference between there and infinity. The superposition principle can be used. That's where we just add all these things together. Can be used to calculate the electric potential for a group of charges. So what we're going to see on this next little video is we have a point in space, and there's a whole bunch of different charges around it at varying distances. So what is the electric potential at that point? And how do we calculate it? So there you go. There's a point, and there's all these charges around it. What is the electrical potential at that location?
According to the superposition principle, the electric potential at a point is the algebraic sum of all the individual potentials existing at that point. The strength of the charges, their polarity, and their distances from the point in the middle completely determine the electric potential at that point. This is because, in contrast to a vector quantity, electric potential is a scalar quantity and has no direction associated with it.
So here's the nice thing about these calculations is we don't care the angles. We only care how far away and what the charge is. Let me slide this over for a minute. This little formula down here, Coulomb's constant charge times the distance we are away, that's the equation they are using, but they just factored out Coulomb's constant. Instead of having to multiply it in by every one of those, they're just saying, hey, you can just factor it all out. Now they referred to another word, polarity. What do they mean when they say polarity? If I was talking about a magnet polarity, what would you tell me? North or south. So if I'm thinking of electricity and I talk about polarity, positive or negative, yeah, that's all it means. The polarity of it is it a positive charge or a negative charge.
Calculating the electric potential at a particular point is simply a matter of finding a scalar sum.
So that's nice and easy. So all they're doing is taking each of the charges and how far away they are, and they're multiplying it by Coulomb's constant. Just add it all up, and whatever that answer is, there's the voltage at that position. Negative 5.1 times 10 to the 4th volts. Am I done? I'm done. You have some time to do some homework.